Thanks everyone for joining and staying back. Very grateful to get the opportunity to present at this IEEE conference. A little bit about myself. I'm a PhD student at the University of Tennessee, working under the guidance of Dr. Travis Humble at Oak Ridge National Lab. I wish to speak today on the topic of reproducibility in quantum computing, which I think is a critical topic, in my view, for the systematic advancement of this field. So first, let me try to lay down the problem statement clearly. So I hope you'll agree with me when I say that reproducibility is crucial in scientific computing. As most of you know, today we are in the NISQ era in quantum computing, where devices suffer from noise and error from various sources. It may be qubit related, it may be the implementation of the gates, or it may be the isolation system. So experiments in general run the risk of being irreproducible. So to investigate this, we need to define the concept of reproducibility. And we use that using Hellinger distance. Now, as you may appreciate, quantum computers almost always produce a distribution and not a single answer, right? And so the task boils down to the ability to compare two probability distributions, which in this slide I call P and Q. Now, there are many such options, but not all of them qualify as a true metric. We like Hellinger distance as it satisfies the triangle inequality and is fairly intuitive. It's a single number that quantifies the similarity between two probability distributions, which are the output of a quantum computer. Now, in this paper, we say that an experiment is reproducible if the Hellinger distance is below a user-defined threshold, which we called H max. And this is the equation 3 that you are seeing on the slide. So if the distance between the two distributions is less than this, one of them is the ideal distribution, the other is what you got out of your quantum computer, then you will call the experiment to be reproducible. In some ways, this work is trying to bridge a gap between the information theoretic measures like Hellinger distance and device characterization data. In particular, our scope is very limited. We are investigating the question of how does initialization fidelity asymmetry affect Hellinger distance. I have not defined asymmetry yet, but I hope you got an understanding of reproducibility from this slide. So now I'll define what we mean by fidelity asymmetry. Fidelity asymmetry arises because the qubits behave differently in ground state and excited state. So the readout error when the qubit is in the excited state, 1, is different from the readout error when it is in the ground state. So this slide, what you see is a subset of qubits of IBM's transmon device called Toronto. 9 qubits are shown, just arbitrarily. And the blue graphs represent the fidelity when the initially prepared state in the ground state is 0. And the orange graph represents the fidelity when the initially prepared state is 1, or the excited state, right? So maybe you can appreciate from this graph that it's a bit risky to quote just a single number like readout, because the blue and orange graphs are quite different. So this graph reflects an asymmetry between the states, which we call it as fidelity asymmetry. So fidelity asymmetry quantifies how differently the qubits behave between the ground state and the excited state in the context of just readout error, nothing else. So I'll not spend too much time on this slide. It's simply a synopsis of all the 27 qubits of the quantum processor Toronto. The takeaway of this slide is simply that qubits display a wide variation in fidelity asymmetry, and qubit 0 for Toronto seems to be the closest to ideal operation, while qubit 24 seems to be the worst. It has an asymmetry of almost reaching 16%. Now, hopefully, in the last two slides, I've been able to convey what fidelity asymmetry means. Now let me take a step back and remind you what the problem statement is again. So the problem we are trying to study is how does the fidelity asymmetry impact Hellinger distance, which is the proxy we are using for the concept of reproducibility. To achieve this, what we did was we built a simple noise model using what is called a binary asymmetric channel. In this figure that you see, F0 represents the probability that you prepare something in the state 0 and it continues to be in state 0. And F1 represents the probability that you prepare something in state 1 and you actually measure that it is indeed state 1. So using this model, we are able to derive a bound for the fidelity asymmetry, which is given in equation 4. I'm not going into the derivation of this bound, but the significance of equation 4 is that the model that we have built, it's claiming that if your device asymmetry exceeds a threshold, which we called epsilon max, if the device asymmetry exceeds that threshold, then the experiment will likely be irreproducible. And so this should be of direct relevance to quantum programmers in the sense that they will like to avoid the qubits which exceed such an epsilon max threshold. Now, this is the test circuit that we use. I'll not spend too much time on this, but it's the one that we use to validate our theory. If you see our paper, you will find that the analysis is done for a general n-qubit register. But for testing our theory, we have used n is equal to 1 for each of the 27 qubits, because in that case, the model is exact with no analytical approximations. And any discrepancies that we observe between theory and experiment is purely the fault of simplistic assumptions. It's not, there is no analytical approximation going on. So this slide shows the raw data for our experiment. The x-axis is the fidelity asymmetry in percentage. The y-axis is the Hellinger distance. There are 27 qubits plotted on this graph, each with a different color. Each qubit, let's take a specific color, say orange. That orange qubit, the experiment is repeated 203 times. So there are 203 dots in that orange cluster. Similarly, there are 27 clusters. Each cluster is representing 1 qubit of Toronto. The horizontal red line, which you see at 4%, this represents the user-specified tolerance on the Hellinger distance. This is what we were calling H-max in the previous slide. So the quantum programmer assigns or decides based on his use case and H-max based on his application. And then the theory that we have developed predicts the vertical red line, which is the maximum asymmetry permissible. So if you exceed that, if the device or the qubit exceeds that, then your experiment might become irreproducible. So for this choice of H-max, in this graph that you are saying, we chose H-max 4%, the theory clearly holds because of the nearly 5,000 data points, only 2 violations occur in this area. And so, for this choice of H-max, we may feel good about ourselves on the analysis front. But not so fast, right? We have not really explored what happens when we vary H-max over all possible values. Does the theory still hold? So to study that, we defined what we call a violation event V. This basically tells you that the data is showing something which the theory doesn't predict. So if the data is showing something which the theory doesn't predict, we call a violation event V has occurred. And we will like to see for each qubit a granular analysis of whether this theory is holding. So that's what I want to show to you next is the results of this violation testing. Once again, the x-axis is the device asymmetry. The y-axis is the Hellinger distance. The line here is the theoretical model that we developed where epsilon max is given as a function of h max. The blue dot represents the quantum processor. It is the average point. The red dots, there are 27 red dots on this graph. They represent the 27 qubits of Toronto. If the theory, the violations, if the red dots lie above this line, then the theory holds. We see that there are 22 register elements which pass the test. The quantum processor itself passes the test, but there are 5 register elements which fail the test. And this, 2 of them definitely fail because they are here on a large H. But then there are 3 of them which lie in kind of the gray region, which is like very small Hellinger distance. And I personally think that, if the user is specifying such a low threshold for reproducibility, then for today's noisy devices, it's kind of not a surprise because the gate error will become comparable to the readout error, and then the theory kind of collapses. So that was basically the crux of the work. So let me conclude here by summarizing. A previous work of ours, we had conjectured that computational reproducibility is impacted by device metrics like initialization fidelity. In this work, what we have tried to demonstrate that conjecture and sort of bridge the gap between hard device data and information theoretic measures. And we hope that this work will be useful in fields like fault-aware compiler architecture design. Thank you so much for your patience, and I'm happy to take any questions if you have.
Thank you, Samudra.